Hello, everyone. Today we're going to talk about Lesson 9, double replacement reactions. You might remember that when looking at single replacement reactions, the very first thing that you should do is check the activity of each metal or non-metal against the activity series. So in this case, we're going to be comparing aluminum with nickel. So if we come over here, we find on our activity series, here's nickel. Here is aluminum. So aluminum is more reactive than nickel, meaning nickel needs to be by itself when this reaction is over. Currently, nickel is bonded to sulfate ion. So this reaction will occur. It will take place, resulting in nickel being by itself. Now, aluminum with its +3 charge and sulfate with its 2- charge will form a compound Al2SO43, or aluminum sulfate. Nickel, as a reminder, will end up by itself. In our second example, this time we're going to compare lithium and hydrogen. I mentioned this in our last session that it might be helpful to think of water as an H+ and an OH that are joined together. Since lithium is a metal and forms a positive ion, it would replace the hydrogen in water. So let's take a look at hydrogen and lithium. So if you look at our chart here, lithium is up here, hydrogen is way down here. So lithium is definitely more reactive than hydrogen. So that way, hydrogen should be by itself at the end of this reaction, which it is. And in this case, we're going to have lithium replacing the hydrogen. Lithium has a 1+ charge because it's in group 1. Hydroxide has a 1- charge. That's the polyatomic ion. Remember, you can always look back at your common ion sheet. If we pair these two up, we get 1 lithium, 1 hydroxide, and then finally balancing the equation, we need to add in coefficients of 2 in front of the lithium, water, and lithium hydroxide. Now let's take a look at problem number 7. In problem number 7, we're looking to compare copper and iron. And the reason why we do this first is exactly for cases like this one. In this case, if we look up the activity of copper and the activity of iron, we'll find out that copper is a lot less reactive, meaning when this reaction is all done, copper should be by itself. Well, when you look at the reaction, you'll notice that copper is already by itself. And because of that, no reaction will occur between copper and iron sulfate or iron 2 sulfate. In example number 8, we have the reaction between zinc and water. So again, if we think of water as an H and an OH, we're going to compare zinc and hydrogen. So in this case, we compare zinc, that's right here, to hydrogen, which is right here. We'll find out that hydrogen is lower down on the table, meaning at the end of the reaction, it should be by itself. Zinc will, of course, react with water to produce zinc hydroxide, ZnOH2, and hydrogen gas. And finally, with problem numbers 11 and 12. In problem number 11, we have powdered aluminum reacting with iron 2 nitrate. Here's aluminum. Here's iron. Remember, the element that's lower down is less active and should be by itself at the end of this reaction. So in this case, iron ends up by itself. When aluminum pairs up with nitrate, aluminum is 3+, nitrate is 1-. So we need 3 copies of nitrate for each aluminum. Next, we have bromine reacting with an aqueous barium iodide. This is one of the few examples that we saw where we have an anion replacing an anion. So we have something that forms a negative charge. So we're going to compare that not to the barium, but to the iodine. And if you think about what it looks like on the table, we have F2, Cl2, Br2, and I2. So we're going to compare Br and I. Here's Br, here's I. I is lower down, so I should end up by itself, or I2 should end up by itself at the end of this reaction. So we will have a reaction here so that iodine ends up by itself. So bromine will replace the iodine. They have the same charge, so the formula is going to look very similar, BaBr2. And you can see here that iodine ends up by itself. So as you can see behind me, when we have a double replacement reaction, two compounds will react, forming two new compounds. Now, unlike single replacement reactions, we don't have to worry so much about reactivity, but we do have to concern ourselves with solubility. Because what will end up happening is if all four of our substances are soluble, that will be an instance where we have no reaction. Let's take a look at an example double replacement reaction.
In our demonstration, we are going to mix two colorless solutions, lead 2 nitrate, which is on the left here, and sodium iodide, which is on the right. So it's important for you to realize that solutions often look very similar to what water would look like, so completely colorless. However, they contain, in this case, a potentially deadly component. So what we're going to do here is combine them in this third beaker. So I'm going to begin by pouring in some sodium iodide. Now I'm going to add some lead 2 nitrate. This reaction forms a precipitate, a solid. So once I add the lead 2 nitrate, you'll notice that the solution immediately turns this yellow gold color and a solid forms. So over time, that solid will settle on the bottom of this beaker and the top will clear up once again.
Now let's take a look at the equation for this demonstration. We started off with sodium iodide solution. Sodium iodide, we'll learn, is an aqueous compound. And we'll combine that with our lead 2 nitrate solution, so PbNO3 2, which is also aqueous. It actually forms two new products, one of which is aqueous and breaks up. So that is NaNO3. And our second product was that bright yellow precipitate, which is known as lead 2 iodide. So just so everyone is aware, a precipitate is a solid that forms as a result of a chemical reaction, and it's abbreviated often as PPT. Next thing we want to do is balance this equation. So we have one sodium, we have one sodium, we have one I, we have two I's. So we're going to go ahead and put a 2 in front of the sodium iodide. So now I have two sodiums. So I need to put a 2 in front of the sodium nitrate. Two nitrates, two nitrates. So now we're all balanced. Before we take a look at some examples, let's go over the solubility rules and what this means. So if you notice, I have two distinct groups of rules on this solubility rules table. The top part tells us whether or not a compound will be aqueous, whether it will dissolve in water. So for the top part, I suggest that you write AQ. So when you're using this rule sheet, what you're going to do is you're going to identify the two parts of a compound using one or perhaps two rules. Please be aware that the rules do not conflict with each other. Even if it seems like they do, I assure you that they don't. Now, let's take a look at a few examples. In our demonstration, we used a solution that I said was aqueous, and that was sodium iodide. So sodium iodide is made up of two parts. Sodium, which is a group 1 element, and iodine, which is a halogen, which is the fancy name for elements in group 17. I should also mention that when a halogen forms an ion, it gets an IDE ending. So chlorine becomes chloride, bromine becomes bromide, fluorine becomes fluoride. So as a result, they took the word halogen and said, oh, we'll call them halides. So we can also think of this word when we're thinking of elements in group 17 as ions. So if we look at the first part of this formula, sodium. Sodium is in group 1. So we know that all compounds of group 1 and NH4 plus are soluble, which is why we were able to write AQ next to the formula for sodium iodide. Our second reactant was lead-2 nitrate. So what you're going to do when you look for a rule is you're going to start with each part of it. Is there a rule for lead? Is there a rule for nitrate? So first, if you look down, you'll notice that there is no rule specifically for lead. Now, some of you are saying, but I see lead right over here and here. So these are rules for different elements or different polyatomic ions that have an exception for lead. So all halides, that's a rule for halides. All sulfates, that's a rule for sulfates. So what this is saying is all sulfates are soluble except if that sulfate happens to be bonded with lead. Well, lead is not bonded to sulfate here. Lead is actually bonded to a nitrate. So just because it has a lead in the descriptor doesn't mean the rule is for lead. The rules are over on the left side here. So these are rules for carbonates and chromates and hydroxides and phosphates, sulfides and sulfites. They are not rules for these guys over here. These are exceptions to whatever the rule is. Exceptions to whatever the rule is. So let's take a look at our rule for nitrates, since there is no rule for lead. We find that all nitrates are soluble. That's great. That means that we can write AQ for lead-2 nitrate. Now, on the product side of our demonstration, we had two compounds. We had sodium nitrate and we had lead-2 iodide. Let's first look at sodium nitrate. Sodium is a group 1, so all compounds of group 1 are soluble. Notice also that all nitrates are soluble, so definitely we're going to write AQ for sodium nitrate. Now, let's look at the rule for iodine, which is actually a halide because it's found in group 17. So the rule for halides says all halides are soluble, meaning we would write AQ, except when paired with silver, lead-2. Well, that's a problem because that's what we have here. We have lead-2. So this exception causes the formation of a precipitate, and that's why we write the little S for solid next to our formula for lead-2 iodide. Now, the part that students find confusing is they believe that there's going to be some exception. So I assure you there is not. So if you look, for example, at the two things that it says all compounds of group 1 and all nitrates are soluble. So if you look through these, you'll find out that group 1 is always an exception to these guys. So down here, these are things that are solid. So for the most part, all carbonates are going to be solid, meaning insoluble. They don't break apart. They form a precipitate and settle down at the bottom, except when we have a group 1 and NH4. And of course, it has to be an exception because all compounds of group 1 and NH4 plus are soluble. Same thing here. All chromates are solid, except those of group 1, NH4, and a few others. Same. All hydroxides are insoluble, meaning we would write S for solid, except when they're paired with group 1. Now, the other question is, it says all nitrates here are soluble, but there's no mention of nitrate down here. Doesn't that conflict? And the answer to that is no, because all of the examples down here are anions. They're negatively charged. So carbonate is CO3 with a -2 charge. The reason why we don't have to write all nitrates as an exception down here is because nitrates are also a negative charge. So these two are not going to pair up because they repel each other. So we don't have to make an exception for it because it's never going to happen. Okay, let's go ahead and take a look at some of our examples. And we'll keep referring back to these rules. So if we go back and look at our general equation, one of the things that I want you to notice is this. The outside parts of the compound will bond together. So A will bond with Y from the opposite compound. So the cation of one and the anion of the other will bond. Same thing down here. The cation of one compound and the anion of another will bond together. So we'll have new products of AY and BX. AY and BX. Basically, the two parts that are blue, the anions, will switch places with each other. So in this first example, if you consider that the barium and the carbonate will bond together to make barium carbonate, Ba is 2+, carbonate is 2-, so 2+ and 2- cancel each other out. The second part that will bond together is potassium from potassium carbonate and chloride from barium chloride. They will form a second compound known as potassium chloride, A+, Cl-. Some of you are saying, what happened to the 2's here? How come we didn't write those 2's in? Remember that when we form new compounds, we don't care how many copies of them are on the left side. We determine the formula by looking at their charges. A +1 and a -1 form KCl, one of each. We will worry about balancing the equation after we write down our final products. In this case, when we balance this equation, we wind up with one barium, 2 chlorides. So we need to put a 2 in front of potassium chloride, 2 potassium, 1 carbonate, 1 carbonate. So all of the rest of my coefficients end up being 1s. The last part, assigning the states of matter. So for barium carbonate, we're going to go back and look at our rules. So here are the rules that we're going to use. And if you notice, we have a rule for carbonates. By the way, there is no rule for barium. In a few places, barium is an exception, but there's no rule specifically for barium. So all carbonates are insoluble except, well, barium is not an exception, so barium carbonate is going to be insoluble, meaning that we're going to write in S for barium carbonate. Now, for potassium chloride, there are actually 2 rules that apply. We could use this rule that says all group 1s are soluble, or we could use this rule that says all halides are soluble as long as barium is not one of the exceptions, and it's not. We could also use this rule that says all halides are soluble as long as potassium is not one of the exceptions, and it's clearly not. So for potassium chloride, we're going to write in AQ. Let's take a look at example B. In this case, we have zinc sulfide, which is a solid, reacting with hydrochloric acid, which is an aqueous solution. So when we get our products, remember, we're going to combine the outer parts and then the inners. So the outer parts are Zn and Cl. Now, the charge on Zn is 2+. You can find this on your common ion sheet. And the charge on Cl is 1-. So when they combine, they'll form ZnCl2. Our second product is going to be the combination of hydrogen and sulfide. Hydrogen and sulfide. Hydrogen is +1, sulfide is -2. And they combine, we will get H2S. Balancing this equation, we have 1 zinc, 1 zinc, 1 sulfur, 1 sulfur, 2 hydrogens, so we need to put a 2 in front of HCl, and then 2 chlorines, 2 chlorines here. Finally, to finish off this problem, let's talk about states of matter. So for zinc chloride, we look at the rules. There is no rule specifically for zinc, but there is a rule, again, for halides, because chloride is a halide. Any of the elements in group 17 are halides. So all halides are soluble except silver, lead 2, mercury 1. Well, we don't have silver, lead 2, or mercury 1. So this is going to be soluble. So we're going to write AQ. The second part is hydrogen sulfide. This is a little trickier. So for hydrogen sulfide, we're going to write G for a gas. In fact, there are 6 gases that we are going to be on the lookout for. So if we see one of these 6 gases, we're going to recognize it as a gas and be able to write that down. These are compounds that are gases. Here's the list of 6. Don't worry about it, memorizing it, because I'm going to provide it to you on a set of reference tables. If you see one of these 6 compounds on the product side, you should be able to identify it as a gas. Again, not something that you're going to have to memorize because I'm going to provide that information too. Let's take a look at example number 2. An acid and a base react to yield water and another ionic compound known as a salt. A salt doesn't have to be just table salt, NaCl. Pretty much any ionic compound that forms can be considered a salt, just a combination of positive and negative ions. So if we look here, we have H combining with OH, so the outer parts here combining. That gives us water, plus Na combining with Cl. That gives us NaCl. Na is +1, Cl is -1. By the way, H and OH, +1, -1. When we balance this, we'll find out that all of our coefficients are 1. So 1 hydrogen plus 1 more hydrogen is 2. There are 2 hydrogens. 1 Cl, 1 Cl. 1 Na, 1 Na. 1 O, 1 O. So perfectly balanced. The last thing that we have to do is assign states of matter. Now, sometimes we have to use what I like to call common sense. For water, we know that at room temperature, water is a liquid. So there is no rule about what to call water. We just have to think about what temperature it is at in order to determine whether water would be a solid, a liquid, or a gas. In this case, water is going to be a liquid because there's no indication that there is an elevated or reduced temperature. Finally, for sodium chloride, sodium is a group 1 compound, chloride is a halogen, so we can use the rule that all group 1 compounds are soluble. We can go ahead and write AQ here. Okay, let's take a look at the homework. So in the homework assignment, again, we are going to be predicting products. And in this case, what we're going to do is we are going to use our solubility rules to determine what state of matter our products are in. So first, what we're going to do is look at our acid. This is oxalic acid. Oxalic acid and KOH are both going to be aqueous compounds. Now, when we do this on a test or a quiz, I'm usually going to give you the states of matter for the reactants because you're going to be using that to predict the states of matter and the products. Okay, combining outside portions. So we have an H combining with an OH. H plus and OH are going to make water. We'll talk about state of matter in a second. And then our second product is going to be the combination of potassium and oxalate. So potassium is +1. Oxalate, remember, is a polyatomic with a -2 charge. So again, that can be found on your common ion sheet. And finally, we're going to put those two together to make K2C2O4. Balancing our equation. We have 2 H's plus one more is 3 H's. So we're going to need a combination here of one more H to get 4. So we'll get 4 H's here. 2 OH's. So these two OH's and 2 H's are going to make 2 waters. And then 2 potassium and 1 oxalate will make K2C2O4. So the rest of our coefficients will be 1. Lastly, we have water, which is a liquid, and potassium oxalate. Potassium is a group 1. So we can go ahead and write aqueous. And then the second thing that I would like everyone to do is below our examples, if it's not already done for you, please write out the terms in words. So we have oxalic acid plus 2 potassium hydroxide yield 2 waters plus 1 potassium oxalate. Now let's look at example number 2. In this case, we have cadmium bromide reacting with sodium sulfide. The charge on cadmium, you can tell, is +2. Bromine is -1. There are 2 bromines here. So cadmium has to be +2, or 2 positive, and it's combining with sulfide, which is 2 negative. So we'll get CBS as our product. For the second product, we'll take the Na from sodium sulfide and the bromide, +1 and -1 charges. We'll combine those to get sodium bromide, NaBr. Balancing our equation, 1 cadmium, 2 bromines. I need 2 bromines, so I have to put a 2 here. 2 sodiums, 1 sulfide, 1 sulfide. So these end up being 1s. Finally, we take a look at our rules. First of all, starting with sodium bromide. Sodium is a group 1, so we know this is going to be aqueous. Halides are also aqueous. For the cadmium sulfide, we have to go back and check our rules. So if we look, there is a rule down here for sulfides. All sulfides are insoluble except group 1 and 2, that's not cadmium, and NH4, that's not cadmium. So in our case, we're going to have cadmium sulfide as a solid. Writing out our expression here, we have cadmium bromide plus sodium sulfide. It's going to form cadmium sulfide plus 2 sodium bromide. Okay, let's have a look at our third and final equation on this slide. So in this case, we have sodium hydroxide. It's going to be an aqueous solution because of the sodium, and iron 3 nitrate, which is going to be an aqueous solution because all nitrates are soluble. When we get our products, outers, so Na plus NO3 minus, that's going to form NaNO3 plus inners, Fe with a 3+ charge. We know that because It originally has 3 nitrates on it, so -1 each, that's -3, so this has to be +3. And OH, which is a -1 charge. We get a formula of FeOH3. Balancing this equation, I know I need 3 hydroxides, so I'm going to put a 3 in front of sodium hydroxide. Gives me 3 sodiums, so I'm going to put a 3 in front of sodium nitrate. 3 nitrates, which is what we have here. 1 iron, which is what we have here. This is a 1, this is a 1. Finally, states of matter. Group 1, soluble, so we write AQ. We could have also set it based on the nitrate, also soluble. For the iron 3 hydroxide, we have to go and check our rules. So if we go back and look at our rules for hydroxides, all hydroxides are insoluble. Let's look for iron 3, except those of group 1, nope. NH4 plus, nope, 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 nope. So there's no mention of iron 3 as an exception. So because of that, we'll say that iron 3 hydroxide is a solid. Writing out our formula, we have 3 sodium hydroxide plus 1 iron 3 nitrate, or you could write ferric nitrate, forms 3 sodium nitrate plus 1 iron 3 hydroxide. Okay, let's take a look at 3 last problems here. We have silver nitrate combining with potassium chromate. When you are starting with equations in Word format, one of the things that I would suggest to you is that you convert them into formulas. It's much easier to identify what the products are based on the formulas. So silver nitrate, Ag is +1, nitrate is -1, so we get AgNO3 plus potassium chromate. So potassium is +1, chromate is -2, so we get K2CrO4. We need 2 copies of potassium, which is only +1, in order to balance out the chromate. So K2CrO4 goes to form. So now we're going to combine the outers, so silver and chromate. So Ag plus CrO4 2 minus. So we get Ag2CrO4 plus, in this case, potassium and nitrate. So K plus NO3 minus. So we get KNO3. Again, don't worry about the fact that there are 2 Ks until afterward when you're balancing. Now, speaking of balancing, we have 1 silver, 2 silvers. So I need to put a 2 in front. I can also put that on my top equation. I have 2 nitrates now. I need to have 2 nitrates. So I can put a 2 out in front of potassium nitrate. 2 potassiums, 2 potassiums, 1 chromate. Remember, chromate is this whole thing, CrO4. 1 chromate, CrO4 over here. Looking at our solubility rules, we have AQ, because all nitrates are soluble. So we can also go over here and write AQ, all nitrates are soluble. Here we have a group 1 potassium, so that's going to be soluble. And now we're going to look for silver chromate. Well, if we go back and look at our rules, we do have a rule for chromates. All chromates are insoluble. Let's look for silver, except no silver. So what we're going to do is go back. We're going to identify silver chromate as a solid. Finally, we can drop in our other coefficients. We can write the 1 up here. Now we're just going to name these 2 pieces up here. So we have 1 silver chromate and 2 potassium nitrate. Let's have a look at number 12. Number 12, we have ammonium chloride combining with cobalt 2 sulfate. So ammonium is NH4 plus, chloride is 1 minus. These combine to make NH4Cl plus cobalt 2 sulfate, cobalt 2 plus, sulfate 2 minus. So we get COSO4. Next part, we're going to combine the outer portion, so the ammonium and the sulfate. So ammonium is NH4 plus, sulfate is 2 minus. So we need 2 copies of ammonium to bond with our sulfate. And in our second part, we have cobalt 2 plus and we have chloride. So cobalt 2 plus and chloride are going to make cobalt 2 chloride. We'll identify that charge as well. Let's balance this equation. So we have 1 ammonium, NH4. We have 2 ammoniums. So we need to go ahead and put a 2 in front of ammonium chloride. Now we have 2 chlorines. Over here we have 2 chlorines. That's good. We have 1 cobalt. We have 1 cobalt. We have 1 sulfate, SO4. We have 1 sulfate over here, SO4. Perfect. Next thing, identifying the solubility. So first, we're going to look for ammonium. So if you look for ammonium in our rules, it says all compounds of group 1 and NH4 plus are soluble, meaning that we're going to write AQ for them. So in this case, where I have ammonium, I'm going to write AQ. In this case over here, where I have ammonium, I'm going to write AQ. Second, let's look at a rule for sulfates. All sulfates are soluble except, now let's look for cobalt, not cobalt. Nope, 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 nope. So all sulfates are soluble. So we're going to write AQ over here as well. Finally, let's take a look at the rule for chlorides. So chloride, remember, is a halide. So let's see if cobalt chloride is an exception. So all halides, including chloride, bromide, fluoride, all halides are soluble, which means we write AQ, except Ag plus, not cobalt, lead 2 plus, not cobalt, mercury 1, again, not cobalt. So we have our first example where both of our reactants are soluble, both of our products are soluble. In that case, what I want you to do is to draw an arrow going backwards and then somehow identify that as a no reaction. So some of you are saying, wait, how can that be a no reaction? Let's take a look. If we look at ammonium chloride, floating around in solution, and then we add to that cobalt 2 sulfate, also floating around in solution. On the product side, I have the same thing. NH4 plus, Cl minus floating around, CO2 plus, SO4 2 minus floating around. All of the ions are floating around in this solution, but none of them are bonding to each other and forming a precipitate. Therefore, no chemical reaction takes place. Nothing new is formed. Essentially, nothing happens at all. Okay, let's look at our last example. In this case, we have lithium hydroxide. Lithium is +1, hydroxide is -1. LiOH is going to be the formula. For the second part, we have sodium and chromate. Sodium is +1. Chromate, CrO4 -2. When we form a compound from these two, we'll get Na2CrO4. Next, on the product side, we're going to combine lithium and chromate to make lithium chromate, CrO4 2-. So we need 2 copies of lithium. And we'll make Na and OH. So Na is +1, OH is -1. So we have NaOH. At this point, we can begin to fill in our charges and our states of matter. So let's first identify the coefficients and balance the equation. So we have 2 sodiums. So we want to put a 2 here in front of sodium hydroxide. We have 2 lithiums. So we need to put a 2 here in front of lithium hydroxide. We now have 2 hydroxides on the left. We have 2 hydroxides on the right. We have 1 chromate. CrO4 is one thing called chromate. We have 1 of them on the right. We have 1 of them on the left. States of matter. Lithium and sodium are both group 1 elements. So that means anywhere I see a lithium, I can write AQ. Anywhere I see a sodium, I can write AQ. Now, some of you might recall, but wait, there's a rule for chromates. Let's go back and take a look at that rule. The rule says all chromates are insoluble, meaning we would write an S, except those of group 1. And that's exactly where sodium and lithium are found, in group 1. So when you are an exception to this rule, you end up getting labeled as aqueous instead of being a solid. So finishing off this, we just carry our coefficients up here. Same thing here, a 1 here and a 2 there. So we'll write 1 lithium chromate and 2 sodium hydroxide. Now, just like we saw in the previous example, if everything is soluble, that's an example where we have a no reaction. So often I'll tell students to draw the arrow going both ways, basically indicating that nothing is happening. Just for the purpose of being complete, let me add in our coefficients here. We'll finish off this part. So we have ammonium sulfate and cobalt 2 chloride. That was a lot. I thank you for watching this video all the way until the end. I will post the answer sheet to your homework assignment, so please check that over. Thanks, everyone. Have a great week.